All right, this is chapter 10 of 5 steps to a 5. So this is the first part of the mechanics review that we're going to be doing. This will be super quick, but it leads into chapters 11 and 12, which I think are going to be more important. So this basically deals with free body diagrams and equilibrium. You will not have to draw free body diagrams this year, 2020, on the AP exam. However, you may be asked to interpret them. You may be asked to think about things mathematically or proportionally, where it would be helpful for you to do scratch work of a free body diagram to help you come up with, say, a mathematical model. So, equilibrium by definition is when the net force is zero. That would also mean that you would have zero acceleration, although it does not necessarily mean that you would be at rest. So, you want to think about the way that the forces act on flat surfaces and on inclines, and that can actually help you a lot in terms of thinking about how to determine a force and a value of a force and the direction of a force. So, for example, force of friction in general is coefficient of friction times normal force. But if you have an object, say, that's going in a circular path and on an angle, so on an incline, something like that, like around a racetrack, depending on the speed it's going, it could be where friction is acting up or down. Or, for example, I think if you had a vertical line like this and you were pushing a book, so we're going to have this line and the page as being the wall there. And if the applied force of the book was acting up and to the right, depending on how much the upward component is, would affect whether or not friction's acting upward or downward. If this is a really weak upward component here, the gravity acting on the book downward would be more than the upward component of the applied force, and so friction would have to act upward. If this upward force here is greater than the upward component of the force here is greater than gravity downward, then friction would act downward. If there's no friction, then whichever side has the greater component of force would actually have an acceleration in that direction. So that's an interesting idea. The other thing is to remember that the normal force acts actually, if this was a wall, would act out into the left. So that normal force normally on a vertical surface would be zero. On a horizontal surface like this, if there's no other forces, the normal force is equal upward to the weight downward. Why? Because on a level surface you wouldn't have a vertical acceleration, and so you would have balanced vertical forces. So like I said, I think they go through some of these things, drawing them, talking about components. It is sometimes useful when you have things on an angle to think of it. Yeah, that's about as most of a basic example as you could get. That is an example of normal force, though. And honestly, for free body diagrams, you don't normally draw a box like that. Normally it's a dot or a circle or something like that. So it would be often something like that. And they draw them pretty big, but like I said, you're not going to have to draw them this year. What you do have to be able to do is be able to think about free body diagrams to help you. So tension always acts, it's an internal force. So if the rope is weightless, everywhere in that rope would have the same amount of tension. If the rope does have weight, the tension in the bottom would be greater than the tension in the top. Or pardon me, the tension in the top would be greater than the tension in the bottom. Why? Because the top part of the rope has to hold up the rest of the weight of the rope as well as the weight of this thing. If we assume the rope to be massless, tension would be the same everywhere. So if you have no acceleration with this thing or a constant velocity, again, force up is equal to force down. This is an interesting example here. If you have these angles that are not equal to each other, in general, you would have this be a greater force than this one. Why? Their horizontal parts have to be equal, but this one acting more vertically would carry a greater percentage of the vertical force upward to counteract weight downward. So they could ask you that conceptual question, which of these strings would have greater tension? In this case, it would be T2. talk a little bit about that here. I don't think you're going to have to do equations like that, though. So in something like this difference in horizontal force would be the acceleration acting divided by the mass would be the acceleration to the right. Coefficient of friction formula, rearrangement of that. Again, this is a normal force. It may not be equal to an object's weight if something is pushing down or pulling up from a surface. So in this case, they didn't draw this to scale. This normal force should equal the size of this weight downward plus the vertical component of this applied force from the person. Something like this, again, can be super useful to think about. So if they tell you something is sliding down at a constant speed, there has to be friction in this case. So you could think about drawing this weight as a component, and they're going to talk about that here. So mg sine theta would be the component parallel to the surface. Mg cos theta would be the perpendicular component. So this would be a normal force of gravity. This would be the parallel force of gravity. If you're sliding down at a constant speed, that and the frictional force would have to be the same. So the way that you can get something like that is you would think of the weight as acting straight down. You would think of the normal force as being something like this, and you would think of the parallel force as being something like that. So I'm going to adjust these to God. So this one is the weight. That would be the longest of the three. So this angle here is the same as this angle here. And I could go through that proof with similar triangles. I'm not going to do that. But this is mg cosine theta. This is mg sine theta. Again, you won't have to draw something like this on this year's AP exam, but it may be helpful for you mathematically to realize that, say, this mg sine theta downward would equal force of friction acting upward for an object going at a constant speed. Free body diagrams for things that rotate. Fulcrum is here. You've got a person, Bob, not on the center of the bridge. I think this is pretty good. This lever arm, I think, is a tougher concept. I like to think about figuring out forces like mg sine theta or f sine theta. So essentially, if we have something pulling up and inward, something like this, the vertical component of that force would multiply by this total distance would equal the torque. The lever arm kind of does it just a little bit differently. Like I said, I think it's harder to think about. And they have practice problems at the end. So I don't think that's that important. With those, you can look at those. Most of you have the 5 steps to a 5 on your own.